Everybody. This is Kurt. We're going into the fourth installment of our kinetics unit here, and this is about mechanisms. So, again, we've talked a lot about the rate and how to analyze the rate and figure out the rate law and the integrated rate law and all this stuff. But what does it actually tell us about what's happening in the reaction? If you remember back to the first video, I said that's why we do these kinetics experiments and measure the rate of reactions because it tells us something about the reactants and how they react and the process by which they get converted into products. And so that's where we're going to get into today in this video. So, sorry. So, mechanisms. What is a mechanism? It's the series of steps that a reaction proceeds by. So, oftentimes we think about a chemical reaction, we're given a reaction equation. We've got two ozone molecules, in this case, reacting to form three oxygen molecules. But the reaction doesn't just occur in one step where the two ozone molecules collide and then it spits out three oxygen molecules. So this is not how the reaction actually proceeds. What actually happens is there's two steps to this process. In the first step, we have one ozone molecule that breaks apart to form an oxygen molecule and leaves one oxygen atom by itself. Okay, so it's represented here a little more graphically, showing you the Lewis structures below. This oxygen atom, as you might imagine, right? We talked about oxygen doesn't usually occur as just oxygen atoms. This is actually a really unstable atom. It really wants to complete its octet, so if it bumps into another ozone molecule, which it does in step two, the oxygen atom, when it bumps into another ozone molecule, then turns into two oxygen molecules. Okay, and so that's shown below. We have an ozone molecule, the oxygen atom. This bond right here breaks, and we form two bonds between these two oxygen atoms. Okay, and we're left with two more oxygen molecules. So what you can see is that it still ends up giving us the same overall process, really, right? We start with two ozone molecules, and we end up with three of these oxygen molecules. And if we look at that, that's what we've got. And if we add these two reaction steps together, we should end up with the overall process. That's how mechanisms always work. If I add the steps of the mechanism together, I should get the overall reaction equation back. And just like when we were talking about Hess's law, if something is on the left side and the right side of the reaction equation, we can cancel it out. So in this case, if I add these two together, I'm going to have an oxygen atom over here on the reactant side and an oxygen atom over here on the product side. So I can cancel those out, and then when I add them together, I get 2O3 forms 3O2, right? Again, the overall reaction equation. So these oxygen atoms here that I just canceled out, we call those intermediates. So it's a substance that gets formed in one step of a mechanism, and then in a later step, it gets used up, right? So we're creating an oxygen atom here in the first step, and then in the second step, it gets used up, okay, in forming the two oxygen molecules there. So we would call the oxygen atoms intermediates. And intermediates will never show up in the overall reaction equation because they always will occur on the reactant side and the product side at some point in the mechanism. So when I add up the reaction, they'll always cancel out. So again, this is some interesting information about the reaction that isn't shown if I just look at the overall process. And it's useful to know some things about this because that might affect how a different reaction involving ozone might behave. So just some more terminology. An elementary step is a single step in a chemical reaction, right, in a mechanism that can't be broken down further. So in ozone decomposing into oxygen, like we just looked at, there were two elementary steps there, right, because those steps couldn't be broken down into other steps. A concerted reaction is just a reaction that occurs in one step. So a concerted reaction just has one elementary step. And then there's this term molecularity, which has to do with how many particles are involved in one of those steps. So we have different terms to describe these different number of particles that we could have. So the first step that we looked at, where O3, the ozone molecule, just breaks apart by itself. It's not reacting with anything else. It just is unstable and will break apart. is called a unimolecular reaction because you just have one particle here, one oxygen or one ozone molecule that's breaking apart. In a bimolecular process, we have two things. Like in the second step, right? We had one O3 molecule and one oxygen atom that collided to form products. Okay, so that's called a bimolecular process. Um, we also could talk about a termolecular process. Ter just meaning three, and so here this is a different reaction, but it's a concerted reaction where you just have one step where all three of these molecules have to collide and react all at once to form the nitrogen dioxide that you see on the product side here. You might ask, like, does it keep going? But actually, even termolecular processes or termolecular steps are really, really rare. And the analogy, and so actually anything beyond termolecular is actually so rare that it's statistically impossible. And you could imagine this thinking about how cars get into accidents. You could imagine a situation where a car just runs off the road and collides with a tree, and that would be like a example of a unimolecular process, right? Where you just have one car, it collides with a tree, and that's the reaction where it has its accident. You can imagine a bimolecular sort of car collision where two cars are driving along on the highway, one person cuts the other person off, and the two cars collide, right? So there's two things that are colliding to form this. Again, the accident is the reaction that's happening. And you could possibly even imagine three cars that simultaneously collide all at once. Like maybe somebody runs a red light and just happens to hit two cars that are crossing its path, right? All at the same time. But you would imagine that's pretty unlikely, right? Normally one car would collide into another car and then maybe a third car gets involved afterwards. But it's very unlikely that three cars would collide all at the same instant together, right? And if you take that one step further, four cars colliding, anything beyond that just becomes statistically impossible. Okay, you have to really try to make that happen. So you really only have to worry about unimolecular and bimolecular, and very occasionally termolecular. Related to mechanisms are these things called reaction energy profiles. So this is a representation of the potential energy of the reaction as I convert my reactants into products. So you can see it's got potential energy on the y-axis, and reaction progress is what's listed on the x-axis. And what that means is just as I'm going from left to right on this chart, I'm kind of like moving through time. They don't call it T, but you can think about it that way. So here I start with reactants, I go through all this, and I end up with products over here. Okay, so again, normally when we saw these reaction energy profiles, we just saw reactants up here, products down here, and we looked at the delta H, right? The change in energy, change in potential energy there. But now we're going to take a little closer look at what's happening in between there as well. Each hump that you see here is representing one step in the chemical reaction. So whenever you have a step in a mechanism, you end up reaching these really high potential energy states. And we'll talk about what each point on this chart means, okay? So this is the reaction energy profile for ozone decomposing and forming oxygen. And so we can look at what is represented by each of these points. At point 1 here, we have the reactants. So we just start off with 2 of these ozone molecules. Nothing's happened to them yet. But as they start to react, remember the first step was that one of these ozone molecules is going to spit out an oxygen atom. That was the first step. And so we end up getting first to this point 2, which we call a transition state. A transition state is the highest point of the potential energy in a given step. Okay, so you can see there's 2 transition states, and we'll talk about what's going on at each one. But we'll start with point 2. So what's happening is this bond between these 2 oxygens that's shown with a dotted line is starting to break, but it hasn't completely broken, and so that's actually even a higher potential energy state than once the bond's broken completely. Okay, and that's because if you imagine I don't know, it's something where it's just halfway in between. It's not a very stable situation. And so if we keep going, then the bond will completely break, and we end up with an intermediate right? We talked about this. This oxygen atom is really what we consider to be the intermediate, but the intermediate state that we're at is where all of these things are present. Okay, one of the bonds, this bond between these two oxygens has broken, and we're left with one oxygen molecule, an oxygen atom, and an ozone molecule still that hasn't reacted. Okay, so now we're moving on from here. So again, this is lower in energy than the transition state, but it's still higher in energy than the reactants or the products. Typically, that's how it's going to be. Okay, and so we're still at a higher energy state, and so it would like to get to a lower energy state. That's typically how these things go. And so it's going to go through a second transition state. And if you remember, in the second step of this mechanism, the oxygen atom that we produced ends up interacting with the second molecule of ozone, and we end up getting an oxygen molecule that forms here as a bond forms between these two oxygens, and this bond here breaks. Okay, so as that happens, we end up getting to, again, this unstable transition state where I've got a bond that's breaking here, but it's only gone through like half, it's only half broken at this point, and we have a bond here that's forming, but it's only half formed. Okay, so that's a really unstable situation. We call that, again, a transition state. And as the bond here continues to form and this bond continues to break, we end up getting to products where we just have our three oxygen molecules. Okay? And so you can always look at these reaction energy profiles and count how many steps are occurring by how many humps are here. So each hump, the peak of each hump is going to represent a transition state in a step in your mechanism. And each valley that you see is going to be an intermediate state in your mechanism. So you can get a lot of information by looking at these reaction energy profiles. Some more information that we can get out of them is some of these differences in energy, right? So we obviously talked about what this difference in energy is, and if you aren't remembering what that is, think about it, and I'll explain it in just a second. But I'm first going to focus on these yellow double arrows. So we talked about when a collision happens, it has to have sufficient energy in order for that reaction to occur. And so that's what this yellow arrow is. It's called the activation energy. So it's the energy required to initiate this step from happening. And you can think about a different activation energy being required for each of these steps. Now, you don't need to be able to predict this, but an ozone molecule breaking apart and forming an oxygen atom is a really unstable thing. And so that takes a lot of energy in order for it to occur. So that's why this activation energy is much higher. And it's a much smaller activation energy for the second oxygen to collide with an ozone molecule and produce more oxygen gas, more molecules. Okay? And we can also talk about something called the entire reaction's activation energy. So this is the activation energy of each step. And there's also this thing called the reaction activation energy, which is usually what we're actually concerned with, which just represents the difference in energy of the reactants to the highest transition state, the highest activation energy, basically. So in this case, it's equal to the activation energy of the first step. But if there's a higher activation energy in the second step, like if the second peak was up here, it'd be the difference in energy of the highest peak to the reactants. So we also have, okay, so there we go, spoiled it for you. This is delta H. So this is the difference in energy between the reactants and the products. And we can also see that labeled on the potential energy diagram, the reaction energy profile. Okay, so we've already seen that delta H. So how does this all relate to kinetics, right? We talked about kinetics and how fast reactions happen. And now we talked about mechanisms, right? But how do the two link together? So there's a term called the rate determining step, and it's sometimes abbreviated RDS, and sometimes it's called the slow step. And what that is the slowest step in your mechanism. So when you have a mechanism, not every step is going to occur at the same rate. And in fact, you'll always have a rate determining step that is vastly slower. Okay? The rate determining step is vastly slower than all of the others. And the analogy I sometimes use is, let's say you're trying to make it from Stamford, Connecticut, okay, down to somewhere in New Jersey, and doesn't really matter how long that drive is or where you're going in New Jersey, probably how long that trip is going to take depends on how bad the traffic is in New York City, right? And if the traffic's really bad, then it'll take a long time. If the traffic's really smooth, let's say it's really late at night, then actually that trip won't take very long. And so it's the same way with chemical reactions. One step is always going to be vastly slower than the others. And so it doesn't matter how fast or slow the other steps are. This is really what dictates how fast the reaction occurs. The rate determining step is usually the one that has the higher activation energy. So the highest activation energy step will be the rate determining step. And the reactant order that's in the rate law, remember we said it was not related to the coefficients in the overall reaction equation. Those reactant orders come directly from the coefficients in the rate determining step. Okay, so let's go back and say, what does that all mean? So here's our overall reaction and the two steps in our mechanism, and here's our reaction energy profile. So we've got two steps, and the first step is vastly slower because it's got the much higher activation energy here. So because of that, we can look at this reaction energy profile and identify that the first step is the rate determining step. So knowing that information, I can actually immediately write the rate law. Okay? So I know that that first step is rate determining, and so the rate law is going to be rate equals K ozone to the first power. How do I know it's to the first power? It's because this step in the reactant side includes one molecule reacting to form the products of this step. So if the reactants in the rate determining step, if it only has one molecule of ozone, then it's going to be ozone raised to the first power. If it were 2 molecules of ozone, it would be ozone squared. If it was 3 molecules of ozone, it'd be ozone to the third power. Okay? So what I told you originally is I can't just take the coefficients of the overall process. And you see why that is, right? If the rate is equal to K ozone to the first power, if I were to take it from the overall process, I would assume it's 2, but that's not the case, okay? I can only take the coefficients from the rate determining step and put those into the exponents, the reactant orders in my rate law, okay? So you might say, well, why don't I just take the reaction energy profile, right? That makes it a lot easier. If I have the reaction energy profile and the mechanism, I can get the rate law really easily. Well, the problem is that it always goes the other way. So when I have a reaction, I don't know what the reaction energy profile is, and I don't know what the mechanism is. Chemists take the data that they get in their kinetics experiments, and they figure out what is the rate law. Once they have the rate law, then they propose a mechanism that matches that rate law. So if they have a mechanism with this would be going back just looking at this, how they would do this. So they would do their kinetics experiment, either the initial rates method or using the integrated rate laws. They'll figure out the rate law, and then they'll propose a mechanism, let's say this one, that matches that. Okay? And this matches this rate law because we're assuming this is the rate determining step. Okay? And so that's the way it works. So I do the kinetics experiments, I get the rate law from that data, and then I propose a mechanism that fits that information. So it always goes in that direction, right? In actuality, in the real world. So mechanisms can never be proven, they're only supported. So again, we're saying, well, this is the kinetics data, this is the rate law, right? That's something that we can prove. But the mechanism is something that happens to fit it, right? It's kind of like when you're trying to put somebody on trial for murder, right? You can never, unless somebody on the jury happened to actually see the murder happen, right? You can never 100% say, yes, I know this happened. But you can support that with evidence. And so that's what we do. We do the kinetics experiments, we get the rate law, and that supports the mechanisms that we propose. So there could be many possible mechanisms, and sometimes there are mechanisms that people believe for a really long time, and then when they do later experiments, they find out, oh, that must have actually been wrong. So the kinetics data can be used to prove a reaction that a mechanism is wrong. So just like in a trial for somebody who's on trial for murder, if you find out that there's good evidence to say this person was like in a different country, let's say, during the time that the murder happened, you can pretty confidently say, okay, that person isn't the person who committed the murder. And it's the same way with mechanisms. If I know that the mechanism I proposed should say it's first order in some reactant, but I find out the rate law says it's second order in that reactant, that kind of proves that that mechanism isn't correct. Okay? So let's look at an example. So let's say we've got a chemist performing this reaction, some generic reaction of 2A reacting to form this molecule A2. And they do their experiments and they find out that the rate law is this. Rate equals K times A to the first power. So it's first order in A. They propose that the reaction is concerted. So if you remember, a concerted reaction is one that happens in just one step. So they're saying, is this a reasonable conclusion based on the information given? Explain why or why not. Well, let's look at what's given. We're given the rate law, which says it's first order in A. We're given the reaction, right? That it's 2A goes to A2. And we're given the proposed mechanism saying it's concerted or one step. So that's basically saying that this is the one step to their mechanism. So what's unknown is it reasonable to propose a concerted mechanism based on the information that's given? So again, let's look at this. If the reaction were to happen in just one step, then that would have to be the rate determining step. So our rate determining step here is the overall reaction. It's the same. 2A goes to A2. If that were the case, we would assume that the rate law should be second order in A, because in the rate determining step here, we have 2A reacting to form A2. So it should be rate equals Ka squared. What we actually know is that it's not, right? This is the rate law they experimentally determined, that it's first order in A. So that says that this is not an appropriate mechanism. It's not a reasonable mechanism to propose. Okay? Another example of something you'd be asked to do. Here's the reaction energy profile here matches this mechanism over here on the left. So it wants you to answer a few questions here. The first, so here's the given information again. We'll leave that up. The first question, determine the overall reaction. Okay, well, we're just going to add up the steps. Okay, we cancel out anything that occurs on both sides. Okay, so the B occurs on both sides. The ABB occurs on both sides. And what's left over is 2AB plus C goes to ABBC plus A. Okay, complicated to say, but you can see where I get that, right? Another question you might get asked is identify any reaction intermediates in the mechanism. So again, going back here, that's anything that gets canceled out. So that's B and ABB. Write the rate law for the proposed mechanism. So again, if we're looking at this mechanism, this reaction energy profile shows that this is the slow step here, okay? This is the slowest step. This is the highest activation energy. And again, you might have to be, in this case, it's pretty obvious, and that's the way it'll be, where the activation energy for one step is clearly higher than the other two. And so in this case, the rate law is going to come from that rate determining step, this first step. And so we just have one AB that's reacting in the first step. So the rate law would be first order in AB. Is the reaction endothermic or exothermic? Well, that depends on where the reactants are and where the products are. You see the products are higher in energy, so it'll have a positive delta H. And if it has a positive delta H, that means it's endothermic. And lastly, how many transition states are represented in the reaction energy profile? Well, again, it relates to how many of these peaks we have. We've got 3 peaks, so there are 3 transition states. Okay? Just to recap, that's pretty much it. We'll get into some more catalysis and how catalysts fit into these mechanisms in the next video. But for now, we'll just recap what we did. So reactions don't usually happen all at once. There's usually a series of steps that they occur by, and that is called a mechanism for a reaction. The reaction energy profile shows the energy changes as the reaction proceeds, right? And the shape relates to the mechanism in a few different ways, as we talked about. Each mechanism will have one slow rate-determining step, and that is what relates directly to the rate law of a reaction. And by determining the rate law, we can make some conclusions about the mechanism of a reaction. Mechanisms will never be proven true, only supported, but they can be proven wrong. Okay? So that's it for this video. Hopefully that was helpful, and we'll see you next time.